Hi, I'm Ryan Baker, and this is Big Day in Education.
In today's session, we'll talk about metrics for regressors, linear correlation and its close relative Spearman's rho, the mean absolute error and the root mean squared error, and information criteria such as BIC and AIC.
Linear correlation is when A's values change, does B's values change in the same direction? And it assumes a linear relationship. So it assumes that it's not going like this. So what's a good correlation? 1 is perfect. 0 is no correlation at all. There's just no relationship. -1 is perfectly negatively correlated. In between, what's a good correlation? Depends on the field. In physics, a correlation of 0.8 is something you have to be depressed about. In education, a correlation of 0.3 is something you can be excited about. Why are small correlations okay in education? Is it just that we're inferior to physicists? I'll ask my dad, he's a physicist. Lots and lots of factors contribute to just about any dependent measure. So let's look at some examples of correlation values. As you can see, 1 is just a straight line. It can be any slope except for flat. Couldn't be this either. But as long as it's going up, it's 1. If it's down, it's -1. You can see 0.8 has more spread, 0.4 has a little more spread still, but you can kind of still see a pattern, and 0 is just a blob, and then 0.4 going the other way, -0.4 and -0.8. So as you get more close to 1 or -1, you get more focused. And you can see that all the lovely stuff at the bottom all has a correlation of 0.
Now it's worth noting that correlation tells you how good a linear relationship can fit the data, but it doesn't tell you everything about exactly what the relationship is. That's why it's still good to look at a plot of some sort. Take Anscombe's famous quartet. These 4 graphs all have equal correlation, but they tell very different stories. One of them, the top left, is kind of the classic image we have for a good but not great correlation. There's a line, they're kind of spread out along it. The top right, you can see that although that line fits the data with that same correlation, actually it's completely missing the point that there's a curvilinear function. The third one is a line with the wrong slope but an outlier. And the fourth one is just junk. These all get the same correlation. So correlation doesn't tell you everything, it's just a start. R squared is the correlation squared. It's also a measure, by some fancy statistical voodoo that I won't be talking about today, of what percentage of the variance in the dependent measure is explained by a model. If you're predicting A with B, C, D, and E, R squared is often going to be used as the measure of your model's goodness rather than R. This depends on the community. It's kind of arbitrary which ones communities prefer, but you might see it. Spearman's correlation, rho, is the rank correlation, and it turns each variable into ranks. So 1 becomes the highest value, 2 becomes the second highest value, 3 becomes the third highest value, and so on. You turn the variable into ranks, then you compute Pearson's correlation. There's actually an easier formula, but it's not relevant here. Spearman's rho is popular in cases where you have lots of outliers, or a relationship that's monotonic, but not particularly linear. It's interpreted exactly the same way as Pearson's correlation, with 1 being perfect, 0 being no correlation at all, and -1 being perfectly negatively correlated, just like my Uncle Jerry's tips on the stock market. So why use Spearman's correlation? Well, it's more robust to outliers than Pearson, and it determines how monotonic a relationship is, how much one going up associates with the other one going up, not how linear it is. And sometimes that's what you want instead.
Next, we'll discuss the root mean squared error and its close relative, the mean absolute error. To get at the mean absolute error, you first take the actual value and you subtract the predicted value from it. You then take the absolute value of that. So if the difference is 3 or -3, it becomes 3. And then you average that across all cases. The root mean squared error is very similar, but just a little bit different. Rather than taking the absolute value, you square the difference between the actual value and the predicted value. You average those squares, and then you take the square root of that. So what's the difference between the mean absolute error and the root mean squared error? Well, at one level, the MAE tells you the average amount to which the predictions deviate from the actual values, and that's very interpretable. RMSE can be interpreted the same way, mostly, but it penalizes large deviation more than small deviation. However, the root mean squared error is largely preferred to the mean absolute error, And I'll show you why, and the example to follow is courtesy of my colleague Radek Pelinek at Masaryk University, who in a previous iteration of this course said, no, Ryan, you've got it all wrong, and here's why. And to follow is based on his suggestions. So in Radek's example, take a student who makes a correct response 70% of the time, and take two models. Model A predicts 70% correctness, and Model B predicts 100% correctness. So in other words, this student, 70% of the time they get it right, response of 1, and 30% of the time they get it wrong, response of 0. Model A's prediction is 0.7. Model B's prediction is 1. So I'll ask you to pause the video for a second and think about it. Which of these seems more reasonable? Which of these seems like a better fit to the actual data here? So let's see what the MAE and the RMSE have to say about this student in these two models. MAE first. 70% of the time the student gets it right. In these cases, the response is 1. Model A has a prediction of 0.7, so the absolute error is 0.3. Model B, prediction of 1, absolute error is 0. The other 30% of the time, the student gets it wrong. Response is 0. Model A, 0.7, absolute error, 0.7. Model B, 1, absolute error, 1. So if we compute the MAE, we find that 0.7 times 0.3 plus 0.3 times 0.7, 0.21 plus 0.21, for a total MAE of 0.42. Model B, well, 0.7 times 0 and 0.3 times 1. 0 plus 0.3, so an MAE of 0.3. And if you didn't totally follow that, go back to the previous slide and take a look again. So in other words, Model B, which gives a probability of 100%, matches a student whose actual probability is 70% better than Model A, where the probability of the model and the probability of the student are identical. Something a little weird about that. So the metric's the metric, but do you believe it? Is Model B really better? Now let's look at the RMSE. 70% of the time the student gets it right. Response is 1. In these cases, Model A's squared error is 0.09, and Model B's squared error is 0. 30% of the time the student gets it wrong. In this case, the response is 0. Model A squared error is 0.49, and Model B squared error is 1. When we add it all together, we find that Model A has an RMSE of 0.21, and Model B has an RMSE of 0.3. So Model A is better according to RMSE. The model that says that a student whose overall probability is 0.7 can best be predicted with a probability of 0.7 does better than the model that says that it can actively be predicted with, and to me at least, this seems a little bit more reasonable. Okay, so moving on. A low RMSE is good, and a high correlation is good. Now some cases are pretty obvious. If you have a low RMSE / MAE and a high correlation, you've got a good model. If you've got a high RMSE or MAE and a low correlation, you've got a bad model. What if you've got a high RMSE or MAE and a high correlation? In this case, the model's going in the right direction, but it's systematically biased. For example, your model might say that adults are taller than children. You got the correlation in the right direction. But it says that adults are 8 feet tall and children are 6 feet tall. It's got a pretty high error. What if you've got a low RMSE or MAE and a low correlation? Well, in that case, the model values are in the right range, but the model doesn't capture the relative change. And you can see this sometimes if there's just not that much variation in the data. This is actually a pretty bad case. Sometimes people will treat it like it's good if the RMSE is good, but if the correlation is bad, you've got a problem.
Now let's talk about information criteria. BIC, the Bayesian information criterion, makes a trade-off between the goodness of fit and the flexibility of fit, or in other words, the number of parameters. The formula for linear regression, called BIC prime, is a function of your number of students, or number of data points, and your number of variables, and also of your correlation. So BIC prime has some nice interpretability. If you've got a value over 0, then your model is worse than expected given the number of variables. If you've got a value under 0, then your model is better than expected given the number of variables. And you can use them to understand how significant a difference is between two models. It turns out that with BIC prime, if you have a difference of 6 or 10 between your models, that's equivalent to having a statistically significant difference, according to Raftery. BIC is said to be statistically equivalent to k-fold cross-validation for optimal k. How you ever get optimal k in the real world, I'm not sure of, but, the derivation is somewhat complex. BIC is easier to compute than cross-validation for some model frameworks, but different formulas have to be used for different modeling frameworks. And there's no BIC formula available for many modeling frameworks. So if you want to do BIC on some of those things, like an artificial neural network, sorry, you're going to have to do cross-validation. AIC is an alternative to BIC. AIC stands for, first, an information criterion, ACACE 1971, and later, and somewhat modestly, ACACE's information criterion, ACACE 1974. It's nice when you're the one who invents the method. You can name it after yourself. ACACE's information criterion makes a slightly different trade-off between the goodness of fit and the flexibility of fit. It's said to be statistically equivalent to leave out one cross-validation. So AIC or BIC, which one should you use? Yeah, I mean, as we've talked about before, the difference between k-fold cross-validation and leave out one cross-validation is also a little unclear. And Powers says that the idea of looking for a single best measure to choose between classifiers is wrong-headed. And I would say the same is true about regressors. Regardless of what kind of model you're building, try to understand your model across multiple dimensions, and that involves using multiple metrics. So in the next lecture, we're going to talk more about cross-validation and overfitting. Thank you very much for coming to Big Day in Education. I hope you had fun today. I'm having fun. See you next time.